In today's video, we are discussing about the memory system. As you know that the memory is the next important component after the processor. The processor is the brain of the computer which does all the work. However, the memory unit holds all the data and instruction that the processor uses for its work. So we can see over here the CPU and memory interaction. The processor has the register MAR, memory address register, or memory data register. In memory address register, we store the address from which or to which a word can be read or written into. So this is a unidirectional bus is connected to the memory, that is called the address bus. If the address bus is of k bit, that we can address up to 2 to the power k location in the memory. So it says that if we have 8-bit address bus, then we can have 2 to the power 8 memory locations. 2 to the power 8 memory locations. So address bus tells about the memory addressability. How many memory locations are there? Each location has one address. Whereas the data bus, which is connected to the memory data register, which is bidirectional in nature, this specifies the word length of the CPU. If it's an n-bit data bus, then n bits of data can be transferred at the same time. Whereas the control line passes the control signals like read, write, memory function completed, wait for the memory function completed in this way. The speed of the memory is measured in two ways. One is called the memory access time, another is called the memory cycle time. The memory access time is the time difference between the initiation and completion of a memory operation. Initiation and completion of a memory operation. If a read operation, let a read operation is started at a particular time and ends at a particular time, the time difference between that is the memory access time. Whereas the memory cycle time is the time difference between initiation of two memory operations. Let at time X, a read operation is started, and at time Y, another read or write operation is started, then Y minus S X will give you the memory cycle time. The memory cycle time is greater than the memory access time. We always want to design the memory such that it should be very large, it should be very fast, but with a low cost. So it is a conflicting requirement. We want to have all the facilities, we want to have a very fast memory, very large memory, but with a lower cost. So different techniques are being used to enhance the speed and size of the memory. For example, cache memory is used for to increase the effective speed, and the virtual memory technique is used to increase the effective size of the main memory. So we will be discussing now about the semiconductor RAM memories. We say it's a RAM memory, it's a random access memory. Any of the memory location can be accessed in a constant time, and that is the reason for which we say it is a RAM. Each memory cell can hold 1 bit of information. So if you have memories, with the memory cell can be thought of as a two-dimensional array kind of thing, and each of the cell can hold 1 bit of information. One row is called one memory word. All cells of a row are connected to a common line known as the word line. Word line is connected to the address decoder. A sense and write circuits are connected to the data input-output lines of the memory chip. So it can be viewed over here in this figure. You can see each of the cell holds 1 bit of information, either it is 0 or 1. So in one row, Here in this example, in one row, there are 8 cells numbered from 0 to 7. So this is in one row, we say word 0, word 1, word 2 up to word 15. So that means word 0 to word 15, there are 16 number of words in this memory organization. And each one cell. And to each of the cell, there are 2 lines are being connected. And here you can see the sense or write or read or write circuit is being used. And these are being, the output of these are being connected to the data input or data output lines. These sense and write circuits are controlled by 2 inputs over here. One is called CS chip select. Another is read or write. So here it gives whether to read from these cells or to write into these cells, and which of the cells to be selected will be given through this chip select input. So each of these 2 is 0 or 1 in this. It is being numbered as this. You can see every row has 8 cells. Now we have how many rows? We have 16 rows over here. If there are 16 rows, then we may require 4 bits to decode it. So 4 bits can have the combination 0000, 0001, 0010, 0011. So in this way, it can be up to 1111. So if you have 4 bits, we can uniquely name all these 16 words over here. So this decoder is a 4x16 decoder, because 2 to the power 4 equals to 16. So from 4 inputs, we can decode up to 16 number of words. So there are 4 inputs are over here. If I would have only 8 word lines, then I might require how many decoder? 3x8 decoder. 2 to the power 3 equals to 8. Now talking about the SRAM. 2 transistor inverters are cross-connected to implement a basic flip-flop over here. The cell is connected to one word line and 2 bit lines by transistors T1 and T2. You can see over here how it is being connected. When word line is at ground level, the transistors are turned off. If it is being at the ground level, it is being turned off, it will be connected over here, turn off, and the latch retain its state. In order to read the state of SRAM cell, the word line is activated to close switches T1 and T2. Sense and write circuits at the bottom monitors the state of B and B dash. So this is either 0 or 1 is being monitored over here. So we have 2 different kinds of RAMs over here. We say the static RAM and dynamic RAM. What is static RAM? Static RAM consists of circuits that are capable of retaining their state as long as the power is applied. So as long as the power is there, the data is there. Once the power is off, data will be lost. These are volatile memories because their content are lost when the power is interrupted. Access time of static RAMs are in the range of few nanoseconds. So static RAM are very fast. However, the cost is usually high. However, if you compare with the dynamic RAMs, they do not retain their state indefinitely. So this doesn't mean that this is the static and dynamic RAM both are volatile. However, as long as the power is there, static RAM will retain its state. But dynamic RAM says even if the power supply is there, it will reduce the capacitor as the capacitors are used over here. It will reduce its intensity. The transistors are generally being used as the basic component in static RAM. The capacitors are used as the basic component in the dynamic RAMs. And these contents must be periodically refreshed in case of dynamic RAM. Content may be refreshed while accessing them from the reading. Dynamic RAMs are less costly as compared to the static RAMs. That's the only advantages of dynamic RAM. However, static RAM has many other advantages. It has it takes less power. It has access time is very less. However, the cost is very high in case of a static RAM. Static RAM uses transistors as basic component. Dynamic RAMs uses capacitor as the basic components. If you look over here, suppose we have a memory cell, this is asynchronous DRAM. Suppose this is the memory cell is organized as 4096 into 512 into 8. 512 into 8 is the same 4096. So this is arranged in form of a two-dimensional array. So we require a row decoder to find the row address. Then we require the column decoder to find out the exact location. Then we use this sensor writer, read or write circuit to read or write into these locations. Now, what we have done? We have row address which could be decoded by row decoder, column address which can be decoded through column decoder, and there is a read write latch through which it will go for either read or write of the content. Memory latency is the time it takes to transfer a word of data to or from memory. How much time it takes to read or write from the memory. Memory bandwidth is the number of bits or bytes that can be transferred in 1 second, in one or in unit time. We can say how much amount of data, how much number of bits that can be transferred in 1 second. There are also double data rate SDRAMs. The double data rate SDRAM says the cells are organized into two banks. That means the memory have two banks, two sides, and it is being arranged in the consecutive words are kept in alternative banks. That means bank 0 has word 0, bank 1 has word 1. So in that way it is arranged so that 0 and 1, the word 0 and word 1 can be read at the same time. Here it is an organization, a memory organization. Here it says to implement a 2M cross 32 memory. We want to implement a 2M cross 32 memory, and we have with us 512K into 8. So we have 512K into 8 chips are available. We want to design a memory of 2M cross 32. How you organize it? First, you divide this 2M with 512K. Do remember that M is 2 to the power 20 and K is 2 to the power 10. So 2 to the power 1 into 2 to the power 20 is 2 to the power 21. 2 to the 512 is 2 to the power 9. K is kilobyte is 2 to the power 10. So 2 to the power 19. 2 to the power 21 divided by 2 to the power 19 gives you 4. So this is the 4 number of rows will be there. And 32 bits, 32 by 8 gives you 4. That gives you the number of columns. So 4 rows and 4 columns. So we have arranged in this format 4 rows and 4 columns. So how you have got the rows? By dividing this first address bit with the address one. While dividing the data bit with data, we get the column number of columns. So that number of cells are over here. Each of these cells that you see over here, each one is 512 into 8, 512K into 8. As it is 512K into 8, we require 19 bit for address decoder, and 8 bit can be transferred from each of these cells over here, each of these modules. Now address generated is 2M. 2M is 21. 21 bits is from A0 to A20. So there are 21 bits. Out of the 21 bits, here we require 19 bits over here. So A0 to A18, A0 to A18 is the 19 bits. These 19 bits are given to each of the cell. You can see over here, we have given to each of the cell. Here also each of the cell. So these 19 bits are given to each of the modules. Each of the modules. What is each of the module? Each of the module is 512K into 8. So out of the 21 bits, 19 bits are given to each of the modules. Now rest with the 2 bits. Now these 2 bits, 20 and 19 and 20, 2 bits is given to this decoder. So 2 bit can decode up to how much? 2 to the power 4. So it can decode up to 4 lines. So we have 0, 0, 01, 10, 11. So if you have 2 bits, that can decode up to 4 lines. So the rest of the bits that you have seen is given for this decoder, which can decode up to this number of word lines. Now to each of these modules, the data line is being connected, which to the, this you can see from D0 to 7, because from each cell has 512K into 8. So 8 bits can be transferred to these lines. So D0 to 7, D8 to 15, 16 to 23, 24 to 31. So 31 bits can be, we can get that 32 bit of data over here. Each of these cell is 512K into 8. So to this, each of these 512K into 8 memory cell, one input is the 19-bit address that we can see over here, the 19-bit address for each of the module. We have 8-bit input and output. We can see for each of this module, a 8-bit input and output is there, which is connected to this. So this entire memory is of 2M into 32, whereas each of the module is of 512K into 8. Large dynamic memory systems can be implemented using DRAM chips in a similar way to static memory chips. So memory modules are an assemble of memory chips on a small board that plugs vertically onto a single socket on a motherboard and occupy less space on the motherboard, allows for easy expansion of the replacement. Now we have, we'll go for the read-only memory. Those are the random access memories or RAMs. We'll discuss about the ROMs now. SRAM and SDRAM chips are volatile. Volatile means it will lose the content when the power is turned off. But many applications need memory devices to retain content after the power is turned off. For example, computer is turned on, the operating system must be loaded from the disk into the memory. Store instruction which would load the operating system from the disk. Need to store these instructions so that they will not be lost after the power is turned off. So we need to store the instructions in non-volatile memory. Like we have in our computer, when you switch on the computer, you will see that the light glows from different components of the computer. That is called the power on self-test. And this has some information to load the operating system into the memory. So if a computer doesn't have the operating system installed, it will give an error message that disk boot failure or no boot disk found. So this message came, that means these are some instructions are already written over there. These are written in form of firmwares. Firmware, nothing but these are the ROMs. So these are non-volatile memory is read in the same manner as volatile memory. So separate writing process is needed to place information in this memory. Normal operation involves only reading of data. This type of memory is called the read-only memory because we only read from these memories. So read-only memory is what? Data written into ROM when it is manufactured. The time of manufacture only that is being written and we cannot alter it. It is designed by the manufacturer. The firmware is an example for the same. There is another kind of ROM, it's called the programmable read-only memory or PROMs. It allows the data to be loaded by the user. Process of inserting the data is irreversible. Once it is written, we cannot change it. Storing information specific to a user in a ROM is expensive. Providing programming capability to a user may be better. So it says that initially all the location contains 0. The location where we want to store some data, those can be done by burning the chips or setting to 1 over there. All other will remain 0 like that. Once it is being done, we cannot reverse it. So it is a irreversible process. Erasable programmable read-only memory. So this is another version of these PROMs. Here it says it stored data to be erased and new data to be loaded. So data can be erased and new data can be loaded over here. flexibility useful during the development phase of digital systems. These are erasable, reprogrammable ROM. That means the program, it can be reprogrammed. Eraser requires the exposing the erasing requires the exposure of the ROM to the ultraviolet light. So we cannot do it by this passing the electric current. Rather, the ultraviolet light is required to rewrite the content. And one more thing to be remembered: it has to be physically removed from the device and show it to the ultraviolet light, and this can be reprogrammed. Then it comes the electrically erasable programmable read-only memory, or EEPROM. So it can erase the content of EEPROM. Now, but here we may not require the ultraviolet light. It can be done. It can be erased electrically, and we may not require to physically remove it from the circuit, from the device. There is another kind of memory is called the flash memory. It has similar approach to EEPROM. Read the content of a single cell but write the content of an entire block of cells. So here the entire block of cells can be written. One more thing I want to say about the EEPROM, that we require 3 different voltages for read, write and erase. But here in the flash memory, a block we may not require 3 different voltages over here. Flash devices have greater density, higher capacity and low storage cost per bit. Power consumption of flash memory is very low, making it attractive for use in equipment that is battery driven. So the power consumption is very low over here. This single flash chips are not sufficiently large, so larger memory modules are implemented using flash cards and flash drives. Only thing is that the content of if you want to change the content, the content can be of the entire block of cells, not a single cell. Here, the matter while designing of the memory, as I told you earlier, 3 things that matters is the speed, size, and cost. So we want to have a very high-speed memory, large memory, but with a low cost. We found that static RAM is very fast but expensive. Because of this only, generally this cannot be used as the main memory. Whereas the dynamic RAM is simpler circuits and less expensive, so these are generally being used as the main memory. Static RAMs are used in the cache memory. We will discuss this cache memory later. So static memories are usual. Static memory RAM is generally being used in the cache memory, and dynamic RAMs are generally being used as the main memory. And if we want to store data permanently, we may go for the magnetic disk. The storage provided by DRAMs is higher than the SRAMs, but still less than what is necessary. So we use for permanent storage, we use some storage devices over here. So from this, this is the diagram for memory hierarchy. You can see over here. So inside the processor, you may have registers which stores some informations. You may have the cache memory. Cache memory has 2 levels over here: L1 cache and L2 cache. It is on chip, or we can say off chip cache. There can be multiple other levels of cache as well. In this example, we have L1, L2 cache. Then you have main memory, secondary device, and then we may have the remote disk as well. We can see over here the registers are more closer to the processor. So if processor wants to do something, it will immediately get the data from the registers. If it is not available, it will get it from L1 cache. If it is not available, it will go to L2. Otherwise, it will go to main memory. If it is not available, it will go to the secondary memory. If it is not available in the secondary memory, it will go to the remote disk. So therefore, the data that are present in registers are included over here in the, this is found in the L1 cache. The data that is found in the L1 can also be found in L2. The data in L2 can also be found in main memory. The data in main memory can be found in magnetic disk. And similar data in magnetic disk can be found in the remote disk. This property is called as the inclusion property. So if you look over here, if you go from bottom to top, the speed is increased. The speed of the main memory is faster as compared to magnetic disk. L2 cache is faster than main memory. L1 is faster than L2 cache. Registers are the fastest because it is closest to the processor. Similarly, if you see for the in cost per bit, the cost per bit also increases. The main memory is costlier than this magnetic disk. L2 is costlier than main memory. L1 is costlier than this L2 cache, and registers are the most costly over here. Similarly, if you go for size, then size increases from top to bottom. The size of L1 cache is more than registers. Size of L2 is more than L1. Size of main memory is more than L2, and size of the disk is more than main memory. Size of the remote disk may be more than this magnetic disk. Speed of memory access is critical. The idea is to bring instructions and data that will be used in near future and close to processor as possible. So this is about the RAM, ROM, and the basic memory. Then we'll go for the cache memory technique.